0, 11 from Algebra 1 here. We got simple probability and odds. So we're going to talk about probability of things and odds of things. Probability. What is probability? Probability is the number of favorable outcomes to the total. So that's what probability is. So favorable outcomes to total. It's the ratio. So we'll say ratio of. That's a bad. Ratio of favorable outcomes to total outcomes. And the total list of all possibilities is what we call the sample space. So a sample space, again, is the list of all outcomes. So if I was going to roll a die, there are 6 total outcomes. So the sample space for a die would be a 1, a 2, a 3, 4, 5, and a 6, right? Now, they're all equally likely, okay? So when we talk about simple probability, we're going to talk about I have the same amount of probability of rolling a 6 as I do a 1, as I do a 3, or a 4, or a 5, so on. So the whole idea is that if all of the outcomes are the same on something that's fair, it's equally likely options. So find the probabilities of rolling a 1 or a 5. We're saying we're rolling the die. So how many are favorable? Which ones am I going to say is okay to get? If I'm okay with rolling a 1 or a 5, so what do I say? How many outcomes am I okay with? I'm okay with 2 outcomes, 1 or 5. How many outcomes total are there on a die? 6. So it's 2 out of 6. Or reduce it to 3. I have a 1 in 3 chance of getting a 1 or a 5. What about B? What if I said if I'm going to roll a die and I want to get an even number? How many even numbers are on a die? How many even numbers? 3. How many total numbers are there? 6. That reduces to 1/2. Or 50% chance of getting an even number, right? 1/2, half the time. Now, wait a minute. There's only even numbers and there's odd numbers, right? What are your chances of getting an odd number? How many odd numbers are there on a die? 3. 3 out of 6. That would be a half. And what's a half plus a half? 1. Because, as I have it stated here, complements. It's the events that make up all outcomes. If I took the probability of rolling a 1, a 2, a 3, or a 4, or a 5, or a 6, they're all 1, 6. 1, 6 plus 1, 6 plus 1, 6 plus 1, 6. All of numbers ends up creating 100%, or a 1. Half of the time you can get an even number, the other half you get an odd number. Add those together, it's all the numbers. So the sum of the probabilities for any 2 complementary events is always 1. Complementary events. Rolling the 1, or a 1, or rolling the other 5 numbers. Or rolling an even, or rolling an odd. Together, they make up 1 or 100%. Okay, so now we're going to talk about what happens if we are putting more than just a die. We're doing more than just a die. What we're going to do is we are going to talk about throwing chips into a bag, or a bowl in this case, and we're going to have 5 red chips, 7 blue chips, 6 yellow chips, and 10 green chips. 1 chip is randomly drawn. What is the probability? What's the probability that it will be blue? So again, remember, probability is favorable to total. How many of them are blue? How many blue chips we got in the bucket or the bowl? Says 7. How many total chips are in the bowl? That's 5 plus 7 plus 6 plus 10. So 12 plus 6 is 18 plus 10 is 28. So 7/28. 7 out of 28 chance. Or I think we can reduce that, can't we? Is 7 and 28 divisible by something? They're both divisible by 7. Which 7 divided by 7 is 1. 28 divided by 7 is 4. You have a 1 in 4 chance of pulling out a blue chip. What if I said, I don't care what color it is as long as it's red or yellow? How many of them are red and yellow, or yellow? 5 red, 6 yellow, make how many? 11. So there are 11 out of how many again? 28. I don't think I can reduce that one. Therefore, you have 11 out of 28 chance. What if I said not green? How many of them are not green? Well, if green is 10 of them, there's 28, so 18. So it'd be 18 out of 28, and I think that can be reduced. Divide at least by, what, 2? So 9 out of 14, you have a 9 and 14 chance of pulling a non-green chip. Now, what if we talk about this? Using a tree diagram to help find the probability. It says, using a tree diagram to count the outcomes. School baseball caps come in blue, yellow, or white. The caps have either the school mascot or the school's initials. Use a tree diagram to determine the number of different caps possible. So how many different caps can we actually have? So I kind of have it listed up on top that you have color, you have the design, and then you have outcomes. So if you think about it, how many different colors do we have? Or what are those colors? They're blue, yellow, or white, right? Each color cap can have actually 2 different things on it, right? This blue cap can have a mascot on it, or it can have the initials on it. But isn't the yellow cap the same way? And the white cap? So, how many different blue caps can I make? A blue cap can have a mascot, or a blue cap can have initials. That's bad too. 2 outcomes. The yellow cap has 2 outcomes. The white cap has 2 options. How many total different ways can I make the baseball caps then? 6 different ways. So we have 6 different ways we can make caps. You guys want to sit there and make a tree diagram every time? What happens if we add one more layer to this? What if I said that the logo itself could have a color? That means you would have to branch off each one of these for every single color. Nobody wants to do that, right? So there's got to be a little bit better way, and there is. That better way happens to be called the fundamental counting principle. The fundamental counting principle, it's a little wordy right here, but it says that if event M can occur in M ways and is followed by event N that can occur in N ways, then if the events M is followed by N, so right after each other, you can take the amount of different ways you can choose them and just multiply them together. So it's M times N ways. So wait, let's go back to our baseball cap problem. How many colors were there? 3 colors. Each colored cap had 2 options for initials or mascot. What's 3 times 2? 6. What was our answer? 6. So it works out. It's very nice. I don't have to draw a tree diagram. So use the fundamental counting principle. An ice cream shop offers 1, 2, or 3 scoops of ice cream from among 12 different flavors. The ice cream can be served in a waffle cone, sugar cone, or in a cup. Use the fundamental counting principle to determine the number of choices possible. Choices possible. So we start off with how many scoops? How many different scoops do we have? What's our options for scoops? 3 scoops. 3 options. How many different kinds of ice cream? 12. And the final thing you have to decide is what kind of cone you want or not. So, how many choices there? 3. All I have to do is multiply those together. What's 3 times 12 times 3? Ends up being 108 ways. So going to this ice cream shop, you would have 108 different ways. Now think of it if you chose more than one flavored ice cream at a time. Each scoop can be different, so that could even multiply this up even more. So that's kind of, I think it'd be easier, because nobody wants to make 108 different pieces of a tree, right? That takes a long time. How about Jimmy needs to make 3-digit password for his login on a website. The password can include any digit from 0 to 9, but the digits may not repeat. How many 3-digit passwords are there? Well, Jimmy has to make a 3-digit password. I'm putting 3 digits on here. You can't repeat. How many choices do you have for your first box? How many times when you go to put your first digit in for your password, how many do you get to choose from? It's not 9. It's 10. Why? Because of the 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So yes, you have 10 for your first choice. But once you've chose a number, how many do you get to choose the next time? Now it's 9 because one of them is used up. And then one after that, there's 2 used up, so now you're down to 8. And 10 times 9 times 8 is? $720 different passwords. Think of most of us use a 4-digit password on our devices. You guys could figure that out because it'd be 10, 10, 10, 10. So there's a lot of choices. Odds. Odds are different. Odds are different than probability. Odds is favorable to unfavorable. It's a ratio, sorry. It's the ratio of favorable to unfavorable. So we still have to worry about what we want, but then we put it over what we don't want. So if odds are slightly different than probability. What are the odds of rolling a 2? How many on a die are a 2? 1. How many of them are not a 2? 5. So the odds of rolling a 2 is 1 in 5. The probability of rolling a 2 is 1 in 6. They're different because they mean something different. What are the odds of rolling a number less than 3? Can you roll a 3 then? If it's less than 3? No. That's not what I want. So it's a 2 and a 1. So there's 2 favorable outcomes to that, to 4 other ones, which is 1 to 2. 1 to 2 odds of rolling a number less than 3.